Welcome, ladies and gentlemen, if you're still with us after the first hour, to 140 Years of Quantum Physics, Part 2. The 1930s were a time of promises kept and promises broken, as great discoveries in high-energy physics appeared across Europe and America, and the world prepared for war. Caltech discovered heavy electrons in 1936, and in 1938, Lise Meitner and her lab partner Otto Hahn discovered the secrets of nuclear fission. However, the wheels of war were turning, and Meitner, who was of Jewish heritage, had to flee for asylum in Sweden before her work could be published. Hahn, who knew that if he co-published with a Jewish woman, his career would be over and he had a family to feed, decided to publish the work under his own name and receive the Nobel Prize that should have gone to her. By this time, Einstein has left Germany with the rest of the Jewish scientists and professors in 1933, most of whom had terrible time finding jobs, although Princeton University rolled out the red carpet in 1933 and said, yes, sir, Professor Einstein, sir, anything you say, sir, and made sure that he felt welcome and loved as he rode his bike around campus without socks. It's at this point that the only real question in science becomes, who can beat Germany? War begins in 1938. Germany rolls out the Blitz in 1939, and by 1941, Copenhagen has fallen to the Nazis, where Niels Bohr of the Bohr model is invited out for coffee by his old friend Werner Heisenberg, who's there to charm him with all the wonderful things the Nazi government has been doing in high-energy physics and the marvelous promises of a brand new life, a very lucrative new life, working for the German government. Bohr says, yes, I see, that's very impressive, that's very interesting. How interesting, tell me more. Thanks Heisenberg for the coffee, says, you did the right thing by finding me. I'm really glad you did. Tell you what, I'll call you tomorrow. He goes home and he collects his son, Dr. Niels Bohr Jr., a grown man, also an accomplished nuclear physicist, and his family, and flees the country on the next train. They are out of Denmark before the next morning, when Heisenberg is wondering why Bohr hasn't called. Those of you who've heard this story in class know that Bohr, as he's locking up his lab for all maybe the last time, takes his Nobel Prize, which is made of solid gold, and he's living in a country under surrender. The Germans will never let him take it out of the country. It's solid gold, even if they don't know him by sight. The fact that he's carrying a solid gold Nobel Prize will not only lose him the gold, will probably lose him his freedom. And he finds one material so fearsomely corrosive that, yes, it will even dissolve solid gold, drops his Nobel Prize into the hissing, seething beaker, puts it on the top shelf of his lab. Now, of course, the Germans, when they figure out he's fled the country, are furious at themselves for letting him slip through their fingers, but they're not stupid enough to mess with a frothing, hissing, boiling beaker on the shelf of a Nobel Prize winning physicist. They leave well enough alone. The Boers cross the Atlantic, go straight to the US government, and Bohr says, look, the Germans are trying to build a nuclear bomb. I know exactly what they're doing because my friend Werner Heisenberg came to Copenhagen 3 weeks ago and told me exactly what they're up to. He says, this is a race. We have to build this fearsome weapon before they do, or they're going to get it first. The good news, Bohr says, is that as far as he can tell, they're barking up the wrong tree. As far as those heavy water experiments are going, deuterium is not going to blow anything up by his calculations. And although we are behind them, we may yet win the race if we have superior brain power. High-energy physics in the early 1940s boils down to the Manhattan Project and how to E equals mc squared the mass of 1 kilo of uranium-238 or plutonium into an amount of thermal energy that will wipe a thriving city off the face of the map and give cancer and leukemia to everybody else within a 200-mile radius. Our only excuse for this reprehensible betrayal of humanity is that the Nazis were already well on their way, and if we didn't do it first, they were going to do it, and they were going to do it more. It didn't make Robert Oppenheimer the lead physicist who considered himself personally responsible for getting us over the hump and making that bomb, feel any better. And for the rest of his life, Robert Oppenheimer celebrated VJ Day, victory in Japan, by locking himself into his office and drinking himself into unconsciousness because he could not live with the price that humanity paid for his cleverness. To atone for his sin and for having brought such a force of destruction to a human race who was clearly not morally and ethically responsible enough not to use it, Oppenheimer opened the San Francisco Exploratorium. He tried to make a museum of science that would bring people together to learn about the forces of nature in a positive, sharing way and not to beat each other's throats all the time. It is probably still the best science museum in the country. It's brilliantly laid out. It has fantastic exhibits. Oppenheimer also, in the beginning, in hopes of bringing people together from all corners of the globe and overcoming their differences in the face of mutual human goals, didn't include any maps or any signs as to where the bathrooms were, because he wanted people to talk to other people as they came together and forged new bonds of trying to find a common goal before the end came. Okay, so that one didn't work out so well. He got maps, he got signs to the bathroom. But once we were clear that we were us and they were them, and the Nazis were over, and really it was the commies that were the problem, Berlin was no longer the center of anything except war relief. Paris is still in shambles and trying to rebuild after all the bombs. And at this point, the great discoveries and great papers start to be shared first on this side of the Atlantic as Europe rebuilds. For instance, those heavy electrons that Anderson and Nettermeyer were tracking at Caltech are not electrons at all. They're muons, a completely different creature, although related to the electron. And at circa 1948, we start to get the sense that there's so much more out there than protons, electrons, neutrons, and those photons that Einstein was getting so excited about. However, before we get much past protons, electrons, and photons, let's pause in the 1950s and 1960s with Richard Feynman and quantum electrodynamics, or QED for short. Feynman got his start on the Manhattan Project, cracking safes and playing practical jokes on the censors who read the mail under the great Dr. Niels Bohr, who hand-picked this scraggly little graduate student out of the heap because Feynman was the only one who really had the brass to argue with him. And anybody who knows the story of Rabbi Yochanan and Reish Lakish knows that you can't do any good work in a room full of people who are all going, "Yes, yes, yes, Dr. Bohr. What a wonderful idea, Dr. Bohr." He said, "Get that kid over there, in here, 8 a.m. in the morning," and Feynman, who cannot believe he's been ushered into the presence of the great, and Dr. Bohr and Dr. Bohr Jr. are saying, "What do you think of this?" And Feynman says, "This, I think it's crazy, it's nuts, what about this part here, what about this part here?" And the boards argue with him, and finally, after an hour and a half, Dr. Bohr Sr. says, "There, now it's ready to take to the higher-ups. Okay, kid, you can go." Because Feynman has been pointing out the weaknesses in their plan and the flaws that they need to fix. Feynman wanted to know why it is that opposite charges attract and like charges stick together. I know we're all taught that in middle school. Negative, negative, repel, negative, positive, attract. But why? And Feynman, who was very much an outside-the-box thinker, noticed he replaced about 10 pages of algebra with a squiggly little diagram that looks like this and says, this is what goes in, this is what they make, this is what comes out, we're done now. Figured it out. He called it quantum electrodynamics. That is to say, why electrons and other quanta move, dynamics, the way they do. Here was Feynman's big idea. Electric charge, he said, is code for collecting photons. We're so used to the fact that Benjamin Franklin said there are two kinds of electric charge, we never really think of what it is. Mass is a numerical quantification of inertia, how hard something is to move. Electric charge is an affinity for photons. Feynman said, look, work with me. All electric charges love photons. They just can't get enough of them. There are two different kinds of electric charge. What does that mean? Well, they all love photons. There's nothing different there, but charges have different methods of collecting and storing their photons. Now, in an example that's rapidly becoming obsolete as everyone shifts to the cloud, electric charges collect photons like you and your friends, presumably your older 20-something friends, collect DVDs. This doesn't work with the cloud. You'll see why in a minute. You know you love them. You can't get enough of them. You're always on the hunt for the new ones, and yet new ones are more valuable than old ones. You will gladly take a new episode that you haven't seen before over one you've seen already. So imagine yourself with your DVD collection. Would you like to get a new one for free? Yeah? Yeah, don't give your address and phone number to people on YouTube to get things for free. It's not going to happen, okay? And just as you're not going to give yours up for nothing either. But what about that second season flashback episode? The one that gives the meaning to the phrase partly new episode, the one you've never liked? If there's a mint edition sweeps thriller, the one that's already out in the UK but they haven't brought out in this country yet, would you trade? Now, let's see how this works. Here's our first model, like charges. What's a like? Well, their photon sharing methods are alike. They're alike, that means they're compatible. Let's see how this works. Here comes an electric charge and meets a like charge. Now this electric charge doesn't say, oh, what a lovely electrical being you have. I see the beauty of your neshama. Now this electron has only one thing on its mind. Look, you have photons. They are photons that are not mine yet. Let's see what we can do about that. How does this interaction go? Let's see. Can I have a photon? No. I'll trade you. Okay, so let's watch that trade. Each one of them takes one they never liked anyway, and they throw, and everybody's happy. Wait a minute. How'd that go again? Conservation of momentum here. Whoa, 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 whoa. Okay. So if you throw forward in order to enable that trade, what happens to you? If we've got two charges here and each one throws forward, what happens to them? All right, granted, charges don't talk, they don't have arms, but they do repel. This is called a virtual photon exchange. Let's see that again. Two like charges get near enough to sense each other. How near? Electric field equals kq over r squared. They exchange photons too fast for any instrument to measure. What do you mean too fast for any instrument to measure? Please be my guest. You take a measuring probe and you stick it in between two electrons exchanging data via the electric field at the speed of light. Tell me when you're halfway in between and intercepted the data stream coming at the speed of light, okay? I'm not going to hold the PowerPoint on you, though. It's called a virtual photon exchange, not because it doesn't happen. It totally does happen. It's just virtually impossible to detect. There you have it. That's why two like charges repel. Each one of them is willing to trade an old photon, one they've already seen and never really liked. It has embarrassing gender issues. It's showing its age, for a new one that they haven't seen yet. Now, let's take a look at the second model, unlike charges. What's unlike? They're photon sharing methods. They're both collectors, but they are entirely different species. And that means the interaction is going to look somewhat different. Let's check it out. Want to trade photons? How? Well, easy. I'll throw and you catch. Same as before, right? Puppy has no arms to throw or catch. That's a problem. Well, why don't you come over here so we can both share? Well, that would be perfect, but we have no legs. That is a problem. What do? Poor little electric charges. No legs. Now, it's true that puppies can throw in their mouths. Yeah, you try playing catch with your dog the way your dog plays catch. Go on. Call me when you actually catch the stick. Their photon sharing and trading methods are incompatible. This is where the DVD analogy comes in. Imagine you've just met a fellow collector online. She's smart, she's funny, she's cool, she's got all the episodes you've ever dreamed of. Also, you know each other through a friend of a friend. It really is her. She's not just some internet scammer trying to recruit you for the evils of the internet. Now, would you like to trade DVDs? Sure. Unfortunately, she lives in rural Alaska. You cannot trade because your storage and trading mechanisms are incompatible. You store in a shelf in your room in suburbia, and you trade via UPS, FedEx, and the Postal Service. She stores under her desk in the loft along with her fishing gear, her hunting gear, and her snowshoes, and she trades via ship coming out of the port of Seattle. Nothing goes to the Western Islands off the coast of Alaska that they don't make, grow, or catch themselves unless it comes by boat from Seattle, shipping starting at $50. You cannot trade. However, all is not lost. Cha-ching! Coronavirus vaccine means schools are opening again. You and your online friend have gotten huge financial aid packages at your dream college, and you will be going to school together next fall. And given that she's smart, she's fun, she's cool, and she has the same taste as you in everything, and neither one of you know anybody else on campus, wouldn't it be a great idea to be roomies? What do you think? One problem solved. Now, for the important part. What are you going to pack to take to college? Pause. List the first 5 things you're going to bring to college. All right. Which of you poor suckers said your DVD collection was the first thing you're going to bring to college? Because my 5 were like clothes, toiletries, the computer, your winter coat if you're going somewhere cold, sunscreen if you're going somewhere warm, then maybe the entertainment stuff at the end. I mean, look at this. You gotta be bringing this stuff on the plane with you in a duffel bag. You cannot take more to college than you can lift. Trust me, I moved back from graduate school on my own when my father-in-law was ill and my husband was taking care of him in New York City. I put it in the storage locker, and if it didn't fit in the storage locker shipping cross country, I carried it in my giant black duffel bag through Midway Airport and all the walks to the L platforms. I had the lacerations on my shoulder for a week. I ask you, are you going to be bringing your entire DVD collection? And for those fortunate individuals who said, no, I'm going to leave them all in my room, which my parents are going to leave entirely pristine for the next 30 to 50 years of my life, because they are under no circumstances going to sell the house to provide college tuition for my siblings and me, or heaven forbid, when the last one of us is out of the house, move to a condo in downtown Evanston and give up the giant 5-bedroom house and backyard, or the fine apartment that they can't really afford to not have any equity on. Seriously, come on, your parents are going to be renting your room out the minute you're gone. What are you going to do? That's right. You're going to prune the collection. You're going to check anything that's old, scratched, chipped, not your favorite, or something she's bringing anyway. Okay, everybody practice. Turn the video feed on your Zoom room. Take that DVD, go on, take it, and practice throwing it away. Take that DVD and throw it away. Think conservation of momentum. Taking it, you're throwing it away. What's going to happen to you? Work with me. Work with me. Let's go back to these electric charges. Each one says, I don't need this anymore. They're packing up. They're preparing to move in and be roomies. Beautiful. And now, not only can they exchange one photon, but it is exactly like a DVD player. You can only watch one photon at one time. But when you're done with that, you can put that one back in the collection and you can try another new one you haven't seen. Yes, each one of them has lost a photon, but they've gained an entire library worth of brand new photons, and therefore it was well worth the sacrifice. What do we see? Again, I know the charges don't talk, they don't have teeth, they don't have hands, they're not puppies. What do we see? This is what we see. Here come the opposite charges. Each one tosses aside a photon they don't need, and where does it go? It goes right into our eyes. We see a spark. Think of it. When you're seeing electricity crackle through the sky in a bolt of lightning, you're not seeing the electricity. You are seeing the light. You are seeing the photons shed by those like charges as they ecstatically rush toward each other and prepare to move in and be as attracted as they can possibly get without embarrassing the dickens out of the rest of us. You see the photons they throw away. This isn't a virtual photon exchange. This is a real bout of photon sharing, and herein lies the experimental evidence that proves that Feynman's model is a workable model. Conclusions. Electric charges interact by trading or sharing photons. That is the dynamics of quanta in electricity. Their apparent repulsion or their apparent attraction is the result of this virtual photon exchange. And that's why like charges repel because the trade has been successful, and unlike charges attract because they can't trade, but moving in together is just as good, if not better.